Hello, hello, hello. This video is going to be all about making flat roofs a little bit less flat. So it's going to be very down-to-earth type of a Grasshopper tutorial where I optimize this surface right here, so that there is potential for water flow and water gathering, right? So, of course, depending on different countries, there are different regulations for the slope. And in Lithuania, it is 2%. But in terms of 2%, it's pretty hard to kind of calculate it or to make it, to analyze it, right? So it's better for us to first convert it to degrees. And just online, if you type in slope percentage to degrees calculator, you're going to get this kind of a website, or just type in 2%, convert to degrees, and then here you see that it's actually 1.15 degrees. That's all we need. 1.15 degrees is the minimum slope for a flat roof so that there are no puddles of water. Another thing that I do before I begin is I draw out the perimeter where I will need to divide it. Let's go to shaded view real quick. I draw a perimeter of the whole surface that is currently flat that I will need to divide, triangulate into triangles, and then I mark out areas where I can have, how do you call those, gutters? Like pipes where the water flows into, or areas where the water flows into. So if I just cell PT so that it's easier for you to see, you can see that I have quite a few here. 1, 2, 3, 4, 5, and 6. Wait, 1, 2, 3, 7. That's number 7, right? Right there. So basically I will try to divide up the roof into parts, and all of the parts will be sloping at least 1.15 degrees or more towards those key points that I marked out. That will then translate the water downwards, right? Except in this case where it's going to be a little bit fancier, but don't worry about that. All right, so now if I were to, let's go back to Arctic's pretty. The first thing to do is actually to draw the pattern, and this is a Grasshopper tutorial, right? But this part is manual because we are smarter than any kind of general optimization software out there. So I will draw out the pattern by myself. So I'll just type in cell PT, cell CRV, select points, select curves, invert. So we invert the selection and type in hide, so that it's only points and curves that are indeed selected. And I'll go to the top view. This is what we have, right? So from here on out, I need to draw, and I'll create a new layer and call it interior curves. And I'll make it red. There we go. So from here on out, I need to draw out a pattern that is going to be made only out of triangles, because triangles are always flat and it's very easy to manufacture and calculate. And that pattern will need to be done in a way where all of the edges kind of meet at these key points. So let me quickly kind of start brainstorming and thinking through this. If I see that this part takes too long, I'll just skip ahead. But just to give you an idea, I guess this would need to be a breakpoint, and then here, oops, here we would have our first triangle right here. Our second triangle would be here, which logically would mean that perhaps here we might end up with a triangle, maybe not, we'll see, something like that. Then this is, if I were to draw it like that, this is quite a big surface, which might work out. We will see. We'll see. I'm not too sure about this edge right here. That might be an accumulation of water, so we might end up just doing something like this, maybe. We'll see. Right, then I would do, of course, a triangle here. That's an easy one. And then I would just extend this line, because it's nice to catch directions and do things on an axis. Just extend this line up until here and draw a first triangle here, second triangle here. Like the corners are very, very easy to do, right? Like triangulating the corners, I mean, is very easy to do. And here we kind of end up with a little bit of a messy situation. There's going to be a long boy here, which we don't love, but since the point is so close to the edge, that's what you have to do, right? So it's going to be a long triangle here. Okay. And here I need to rethink. So these two lines I delete, and I will just draw from the midpoint up until here, up until this perpendicular snap. I'll draw a break line, right? Meaning that from here, this is going to be a high point, and this is going to be a low point. So from here, the water will separate either to the bottom side or to the top side. I think that works a little bit better. Yeah, that's going to flow a little bit better. I can't wait for the comments. That's gonna be naughty. Then from here, there's gonna be an easy triangle here, but I'm just thinking like that maybe, or we could do the same thing here. If I were to draw an edge here and grab a midpoint, connect that to perpendicular like so. Yeah. That actually might be, yep, that's a way to go. There we go, like that. Okay, so this whole area is solved. Now on to the last one. So of course this needs to be a triangle. This needs to be a triangle. And then how the hell do we solve this? Don't really want to do that. Okay, let's do it this way. Maybe something like that, that. Not ideal, but this will work. This would work, right? So what we have now is a bunch of curves that are kind of triangulating our surface. And the issue that we have is that some of these curves really need to be split into parts, and we'll come back to that. This is going to be an important thing, but from here on out, let's turn on Grasshopper and let's start grasshopping, right? So what I want to do from this is create a mesh that is made out of triangles that are marked out by me, right, from this network of curves. So here I have already, of course, as per usual, I have already prepared the script that we will be using, and if I get stuck, I just kind of reuse the script, but I will be kind of recreating it and, you know, mimicking the procedure. By the way, if you want the script, consider to become a Patreon supporter, because you get all of the files, all of the scripts, everything that we do on this channel for free. If you become a Patreon supporter, you just get a big Excel spreadsheet, and there's like download links to every single video, right? So with that out of the way, let's first, let's create a bifocals. You don't need to do this. Bifocals is just for your convenience so that you can see the inputs. And let's just create an empty curve component. Like so. Set one curve. Actually set multiple curves, right? Because we want to set all of the red boys. So set multiple curves and make sure to select only the red ones and not the perimeter one, not the blue one, like that, right? So we have our interior curves, and then I'm going to do an exterior curve. Set one curve, bam, like that. And then we are going to find intersections between the interior curves and the exterior curves, right? So for instance, this point right here or this point right here, we're going to find those. And for that, we're going to be using MCX, multiple curve intersections. You can also go to intersect, I guess it's physical, multiple curves. Bam. Never mind, I'm being stupid, sorry about that, because you're intersecting one curve with a bunch of curves, right? So it's not like everything is clumped together into one. So you're going to be using CCX, curve versus curve intersection, right? This one right here, curve. We connect the group of curves to A, a single curve, perimeter curve to B, and we get our outputs, right? Just like that. Then after our outputs are generated, we shatter. Let me make this a little bit like that. Yeah. There we go. We use shatter to shatter the long curve into smaller pieces. Here, by the way, keep in mind that here I have it turned around, right? So in the top we had the long curve, in the bottom we have the small curves. Maybe we should do that. Okay, important note. Let's switch the inputs. And also let me just make them perimeter curve. And this is going to be interior curves, just so that it's cleaner for you and easier to understand. So I switch them up like that. Perimeter is now at the top. Then I connect my perimeter curve to a curve that should be shattered, and my T parameter is going to be the TA output, parameters on my perimeter curve. And in doing so, we get a crap ton of shattered elements, but notice how they are all in separate branches, and that's because it shatters per each line right here, right? And it places just a bunch of copies, you know, of these segments into separate branches. We don't want that. We want all of the TA parameters to be in one big list. So I'll flatten that TA output like so. And in doing so, we get 16 shattered curves. Great, that's what you want. Then we take those shattered curves, and some of them are going to be polylines. For instance, here, this portion is going to be made out of two segments. We don't want that. We want it to be two separate lines. So we will explode the curve like that. We get our segments, again, places it in data trees. We don't need a data tree, so I'll just flatten it. In total, we get 22 line-like curves. Just in case, to be clean, let's remove duplicate lines. Like that. And we end up with 22 again, but you know, it's good to clean things just in case. Okay, with that done, now it's time for us to use a tool that is very, very nice, and it's called Mesh from Lines, right? So it's under Weaverbird. If you don't have Weaverbird plugin, you can type in Rhino, package manager, type in Weaverbird, install, right? Hit OK. It's going to ask you to restart Rhino. You restart Rhino, you're good to go, right? So ViewerBird under create ViewerBird's mesh from lines weave back asks you to give it a bunch of lines for it to create a mesh. And this is where it needs a very, very clean line assembly, I guess. And for that, we will need to clean up the stuff that we have here. Because for instance, these guys are nice, they're fine, but this is no bueno, right? This needs to be two separate lines actually. So I'll just go through this real quick and I'll just split with this. Now there's two lines, and then I'm just kind of split this with this, split this with this. I'm just checking if they're separate. So if all of the lines are separate, this does not take a long time. You can also just simply, oh, and I need to set multiple curves again. You can also just simply keep going with the script, and the moment you see that it's breaking, then you will see exactly visually where ViewerBird mesh from lines breaks, and then you will adjust accordingly. Right. So these are now cleaned up, all separate line segments. I have my perimeter right here that is now split into separate curve elements or line segments. And I have my interior curves. I will merge them. Merge from here. Bam, like that. Easy peasy. Make that smaller. Yeah. And just in case, yeah, of course, it comes in as a data tree. We don't need it to be a data tree, so I'll just flatten it, flatten the output, connect that to the L input, and voila, we get ourselves a mesh, right? So this mesh right here still needs a little bit of love, and also I don't really want it to be a mesh. I want it to be a poly surface, right? I want it to be a BREP. So to do so, we will get face boundaries component. So from this mesh, we extract polylines. Why is that not? Huh. That one's weird. Why are you not working? Hello? You should be working. If I move you here, will you start working? Oh my god, every time I try to record. Okay, give me a second. Okay, I just deleted this line and drew another one and now it works. I don't know. Anyway, it does seem to work, so we continue. From these boundaries, we will find the endpoints. Maybe we don't need to do that actually, because these are already polylines. Let's try doing it this way. I'll just simply explode them. Just explode the boundaries into separate segments. Now they should be well. What's the word? Sorry. The rotation, the rotation of them should be in the sequence. So this is 1, 2, 3 rather than, well, actually 1, 2, 3 also would work. Anyway, we explode them. We use list item like that. Zoom into the list item and press the plus sign. Actually, you only need 3 of the outputs. So line 1, line 2, line 3 for every triangle. Then you use edge, surface, and you build, well, it asks you for 4 inputs. You actually only need 3. It's going to build a triangle either way. And you just connect it A, B, and C. And now if we check it, 1, 2, 3, wonder why did it already create surfaces, like proper surfaces from here. Let me double check. Okay, I didn't know that it's enough for it. Only 2 lines are enough for it to create surfaces, but just in case, let's do three lines. Make an edge surface, use brep join to join them up. And make a brep out of it. Oh, and don't forget, brep join needs flatten either in the input or in the output of edge surface, so that all of them are in the same data stream, in the same list, so that they can be joined up, or else they won't. All right, so this whole script here is kind of done. We don't need that one anymore, and seems to be quite stable. Let me just bake it out real quick and then double check. Yeah, that seems fine. That seems fine. Okay, so that is the first part, right? And this part is basically, what's the word? To generate a surface that you will continue on working with manually, pushing and pulling on the points, right? So now let's create a new layer and call it rooftop or roof surface SRF. Can be black, that's fine. And we just bake this brep into that layer, right? Insert key, by the way, as long as the layer is active, will bake it into that layer. And now we can hide this. Okay. Now I'll move this up like so, just so that it's not in the way. And then I will start messing around with the points, the height of the points. Before I continue doing so, I think it's important for us to create this portion of the script where we will be indicating the slope, as well as what's the, if we're past or not yet, if we have or have not yet reached the 1.15 degree angle, right? So this one comes with me so that I can follow along, or show you how to follow along. And here is fine. And we just kind of do it. Okay. So the first thing to do is to reference in this brep again. Brep. Set 1. Just like that. We explode it. Or is it deconstruct? Deconstruct brep. There we go. We get its faces, and those faces are surfaces, right? So I'll just mark it. This does not, this doesn't do anything. It's just for me. Right. And now from these surfaces, we will be doing a few things. And before I move on, I will just move one of the points of this brep down, so that it's not perfectly flat, so that we can have a read on what's going on. So I'll just hit or select the polysurface, type in solid PT on, solid points on. Select, let's say, this point right here, because I know that that's where the gutter is. And I'll move it down by minus 100 millimeters, 10 centimeters, just like that. So there's one point that is slightly down, and that's it. I'll hit escape. And we have now at least 3 triangles that are tilting, right? This should be enough for us to get a sense of, what is it that we're doing. All right. So the first step is to actually create, let's go bottom up, right? So the first step is to create a vector, right? And a little arrow that would show us, where it, towards where does it tilt, where does the water flow. So I'm going to take the surface and deconstruct it again to get all of the points for each surface individually. I will deconstruct those points into their coordinates, right? And I will sort those coordinates from smallest to highest, right? And together with the coordinates, I will also sort the points. So how do we, let's do it this way. So the output of the sort list here is the Z coordinate from smallest to highest for each corner point of each triangle, while here, together with those coordinates, the points themselves are sorted. So here, the first element of each list, the first point in each list in this output is going to be the lowest point. That's what we want. So I will just do list item and grab, by default it grabs the first one because index 0. So here we have the lowest points on each list, and of course this one is going to be that. With that being said, everything else, since it's flat, it's currently not freaking out, but it just takes basically for the sake of argument random points, except this one, because we moved it down. We know that it's lower than the rest. Let me hide like a bunch of things here so that they're not in the way. Okay, so we have these points, and I'm going to be specifically talking about these three triangles here because that's where we moved the point down. Then I want to grab a center point of each of these triangles and draw a little arrow towards that point. So to grab a center point, I just measure the area and I get my center points. They do need to be in separate data branches because these points come in separate data branches. So I'll right click and graft the C output, the center point output, like so. And then I can just draw, let me just quickly draw a line between 2 points. From here, oops, from here to here, just so that you understand what is it that we're doing, right? So from center points, we are drawing lines towards that lowest point. For this triangle, the lowest point is here. For this triangle, and for this triangle, the lowest point is there. So we're drawing this line. The line is ugly though, so instead we're going to be drawing a vector. And I'm just going to create a vector between 2 points, vector 2pt, from the center point until the end point. And here we get the vector and its length. And I can, at this point, I can just simply do vector display. Vector display, anchoring is from the center point, and the vector is the one that we drew. And now we have the nice little arrows, but it's a little bit shitty that the arrows are just kind of meeting in one point. So I'm going to make them a little bit smaller. And it's very easy to do so because we get the length of the vector right here while the vector is here. So I can just say multiply the vector length by / 0.9, like 90%. Did I use 90%? Let me check. Wait, that's the wrong one. 70%. Okay. 0.7. Sorry about that. 0.7. So now whatever length this is, it's going to be 70% of the way there. And let's just do amplitude. Vector amplitude. So we changed the length of the vector with this one. Vector comes in here. The new value comes in here, and we use that. Voila. So now let me do solid points on. Grab this one because I know that that's where the gutter also should be, and move it down also by minus 150, or sorry, 100 millimeters. And now all of the arrows are just immediately looking that way. So I know that the water is going to be flowing that way, which is nice. That's what we want. All right. With that done, this whole portion is finished, and this is draw arrow portion. Okay, next up, I'll just leave it here. Next up, we have draw text portion. Okay, sure. So let's again measure the area. So we get the center point of this, and let's pull, or is it, no, it's going to be surface CP, surface closest point. So the center points are pulled onto the surface itself like that. I think it's how I did it. Yes. That's how we did it. So we have our area, center points, we have the surface, and it's being pulled. And the reason why we're doing it is because we get the UV point on the surface, and then we can use that to evaluate this kind of the normal vector, the normal direction at that particular point on the surface. In this case, our surfaces are flat, so there are different ways of other ways of how to do it, but this one is foolproof, so to say. So we will just do evaluate surface. Let me make this bigger, just like that. There we go. Evaluate surface. Surface to evaluate is our, well, every single triangle that we have here, and the UV point is, well, the UV point that we got. And from that we get a normal vector, right? And I can kind of show you vector display again. Pew, pew, whoop, pew. And it's very small. It's like 1 millimeter small, but you can kind of see a little arrow there, and it's kind of pointing upwards. And yeah, that's the angle. You know, that's the normal vector. And the normal vector in most cases is going to be just straight up, right? But in other cases, the normal vector will be a little bit tilted. So what we will do is we will measure the angle between the normal vector and vector z, unit z, just like that. And we get ourselves an angle that is, you know, again, mostly zeros, but then we have something that is not a zero. Notice that the angle is in radians, and that is like not normal people values. So let's make them into normal people values that are degrees. Degrees, connect that. And now we get the output, you know, that is much more human, much more readable. All right, with that done, let me just see. Yeah, with that done, we can just simply do a text tag 3D, or sorry, a regular text tag, I guess. I need to think, or rather I need to just, yeah, a regular text tag. Bam, like that. Location is our point on the evaluated surface. Text is the degrees, and you can right click on the text tag and you can make the text larger. So I'll just choose large. And color, you can change the color if you want to. I will not be changing the color. And here you can see that this is larger than 1.15, larger, not large enough, right? So to make this larger, solid points on, I would need to take this corner point and probably lift it up a little bit more. 5 centimeters more. I didn't even need 5 centimeters, but sure. And now this is large enough. It's tilting there, right? That's how it works. That's literally it. Since these are triangles, you know for a fact that they are flat. By the way, you might end up having this problem. You know, so how close it is to 180. All you need to do is just select your surface and type in flip, and then you know, it's going to be correct numbers. Okay. One thing that's annoying me is how many digits there are after the dot. So I'm going to fix that. To round off a number, all you need to do is just multiply it by how many digits you want after the comma. So let's say 100 not how many digits, but 100 would mean 2 digits after the comma. 1000 would mean 3. 10 would mean 1 digit after the comma. So we multiply the degrees by 100. So now we get this value. Oh yeah, I forgot to flip, I guess. No, it's normal, yeah. So we get this value. And then, sorry, my cat is going crazy. And then we make an integer out of this. Like that. Bam. 184, 118, blah, blah, blah. And then we just divide by the same 100, right? And that's it. You get yourselves a nice little indication, right? Easy peasy. All right. So with that done, we are ready to move on to step 3, which is coloring things. And it's pretty and it's nice. And it's, as you can see, very, very simple. So for each surface, I'm going to deconstruct it. Deconstruct brep, like that. And I get the vertices. And from these vertices, I will construct a mesh. Construct mesh from the vertices. It's going to immediately freak out because it does not know how to deal with that. And because it's waiting for us to give it instructions. Here, 3 points are coming in for each data branch, right? And here the instructions for it, if I hover my mouse over this, is Q0123. Q0123 means make a quad, a rectangle, from point 0, point 1, point 2, and point 3. It does not have a point 3, right? There's only 3 points, point 0, point 1, and point 2. So what we need to do is we need to make additional instructions. So panel T, and in the brackets, T is triangle. In the brackets, 0, 1, 2. Or is it? I think this will work. 0, 1, 2. Enter. / T, T, and then in brackets 0, 1, 2. Connect that to F. Immediately makes a mesh. And now all we need to do is just to color the mesh. We will be coloring the mesh according if it's good or not, right? So we will be using a gradient. Gradient. Just like that. Perfect. And for the gradient, we will need the low value, the lower limit, which probably should be 1.15, right? Because anything below that is a no-go. And the high limit at which, you know, it's going to say, yo, your angle is bonkers, I will say around 10 degrees. Anything above 10 degrees is Y, fix it, right? So 5 degrees will be, or not 5, a little bit higher than 5, 6 degrees will be yellow, right? Something like this should work. And then for our parameters that are actually used to color these things, we will be using the degrees that we get from here, right? From the angle. Or you can use the rounded off degrees, but it doesn't matter. I'll just use the regular degrees that we got from here. Yoink, plug that one in, right? Notice that this is a single list while this is grafted, meaning like not grafted, but this comes in as separate entities, right? So what you want is you want to right click on the T input and use graft to force these degrees to be coming in as separate data branches as well, so that they match up with the vertices that are coming in here. I connect that to my color input, and now everything is green, right? And let me hide the mesh for just a little bit and just see if there is anything else I should be hiding. No, not really. Okay, we're good. And now you can see that, okay, everything is green. And if I were to, actually, let me show you this. Show selected, solid points on. Let me just move this by like a meter down. You know, it's red because it's going beyond 10 degrees in this case, right? So it is coloring it properly. It's just that zeros for it are also green. And why is that? Well, that's because here we have the upper limit, right? The upper limit receives a gradient, while the lower limit, anything below 1.15 always will be green. No good, no bueno. We double click on the gradient, we select this green dot right here, and you can see that once you selected this green dot at 0%, there's color left, color right. Color left, I will click on it, expand, and I will choose red color. So anything, I can kind of show you, right? Anything that is less than green, so anything that goes, that's a smaller number than 1.15 is going to be just hard limit red, just immediately red. Hit OK. And now we're cooking. Now it's showing us the correct values. I'll go to the wireframe view, just because in the wireframe view, it's not kind of shimmering, it's not weird. And then I'll start moving things around. So for instance here, this seems to be fine. This seems to be fine. This definitely needs to sink down a little bit. And then it becomes a problem, right? So either this sinks down and these points sink down even more, or these need to lift. So instead I'm going to lift these guys up by 50 more. There we go. Something like that. Then here we have, let's go for -50. That seems to be good. This one 5 centimeters up. Easy to move these guys down. So I'm going to do that. -100. Bam, just like that. And there, you can see that this is kind of high and it shows 3.5 degrees. We can fix that quite soon. The main issue is going to be these areas right here, where we also have a gutter and we need it to move down, but yeah, immediately 7.5 degrees, right? And I assume we have a gutter here, -50, 7.72 degrees. This is still completely flat. That's an issue. I'm wondering where we should move it. Most likely if I just take this point and move it up by 50. That's a no. Okay, this is where it gets a little bit, a little bit trickier. So I think these two need to move down. Oh, there we go. Okay. And this becomes very, very steep. So I'll just move this one down by like 3 centimeters. And I move this one down by also 3 centimeters. That's better. And this needs to be lifted up. Like that. Anything that is very close, 1.2, well, yeah, it's fine, 1.2 degrees. And that's it. At this point, we have ourselves a roof, right? That we can, let me just default, hide those, shade it, or not even shade it, Arctic. Sorry, show move vertical. I really need to find, where was it? I think it was here. Yeah, it's like that. And then this poly surface, not this poly surface, sorry. This poly surface can get deleted. This one is hidden. And now we have ourselves a roof that is, well, it's according to regulations, right? It would pass the test, the building regulation test, and would get the stamp, at least in this area. So this Grasshopper script, as I said before, is available to Patreon supporters. If you were paying attention, it's available to you because you now have it. Don't need that anymore, because you have it. And this kind of concludes the, you know, more of a real world application of parametric design. It's basically making your own life a little bit easier when designing for these things. Okay, next one is gonna be Unreal Engine. Yeah. I'll see you in the next one. Bye.